Hello everyone, my name is Paul James and I'm here to present our project uh, by the name Uganda Computer Graphics-based Diagnostic and Skincare Simulation Platform, and below it is our code name, which is the Computer Science Graphics and Group 5, and we have a ton of the key terms which we shall explain as we go below. Without wasting any further time, let us dive into this. So, first of all, we have to understand that in the current world, we are facing a number of skin issues, skin conditions, skin diseases, which actually take around 30 to 70% in the general population of the developing countries, Uganda inclusive. And when we talk of Uganda itself, in Uganda alone, we by the research that we made, there is only an estimation of 25 specialists, dermatologist specialists, and serving over a population of 45 million people, which leads to under services, or let us say that many people don't receive these services of dermatologist uh, care. And this, because of this lack or this loophole here, it has led to many social media misleads. Let us say many content creators take a chance of this to mislead the public information, as the research suggested. And it says that when these people go online, they usually just advertise anything, any medicine of their choice, for the sake of them getting either followers, views, or making profit out of it. And it has been made that this kind of social content or social media content creators have led to a more dangerous conditions in from the previous, or to those people who use their contents. And this is why we have come up with this to solve this. First of all, let's dive to our key terms. So the 3D face modeling, what is the use of the avatar? Why did we have to use the avatar? What is the use of the 3D? First of all, this one is for the privacy, okay? We are trying to promote what we call privacy here. We are trying to bring up in a way that once someone takes a picture, we only scan out the affected area and then we put it into the avatar and we delete the image immediately, because people have taken a chance of this. Many in the current technological generation, there is what we call data privacy, which need to be promoted. Otherwise, many people have always been complaining that their data has been taken and it has been used without their consent, and it has led to mistrust among technology and the human use. And another thing that we can talk of is explainable AI. Well, explainable AI here, we are just going to tell. It is just going to be in a way that the picture that has been taken, or let us say that the skin condition that has been analyzed, will be easily interpretable to the end user easily by use of heat maps, as we can see, and then GradCam uh, generations, as we can see here, and then the gun. Well, the gun here, we are going to pick the fake image and the real image, compares it, and then it judges which images are fake. Okay, and this is when we come to the real simulation in our work here. The fake image in this case is going to be what the AI has learned. Okay, and then the real image is what the user will take, and then it compares them and finds out which disease is this. That is the use of gun, and then it will display on the avatar. Uh, we can come to our literature review. My colleague has already reviewed a few of this. We just pick them directly from our paperwork and then here. So the first literature review that I made was extra long video visual language model for our scale video understanding. Now, to overcome the bottleneck of limited, this one, the purpose, first of all, we begin with the problem statement of this. Their problem statement was to overcome the bottleneck of limited context, length, and substantial computational and memory costs, preventing the multimodal large vision models from effectively processing extra long hours videos without sufficient loss of fine grain visual information. Now, this one here, they use a technique of what we call uh, visual summarization tokens, which compresses the key value pairs of visual tokens within an interval, allowing the original key values to be offloaded. Now, substantially reduces the memory consumption, and it employs a dynamic compression strategy that customizes the interval size based on the video's information density. And when we look at the limitation of this paperwork, there were no limitations in the paper. Okay, so it was clean, which means this is actually a good paper, and the model used here is accurate or excellent. And then alongside that, I did not stop there. We went ahead and we went to Calico, which is the path focus semantic segmentation. Now this one introduces first of all, the problem statement is introducing the noble task of path focus semantic. So in simple terms, if I'm to say this one here, this paper was mostly telling us how to focus on particular regions or parts of the body or objects. And then it tells you that this part within this object, like let me say if it is the cup, then it will say that this one is the arm of the cup. So when it comes to the face, and then we scan, or let us say when I take a pic in my face, this is how I took it. When I take a pic in my face, it is now going to say that this is the face detected, and it is going to pick that part and puts it on the face of the avatar. Yeah, so that is how I got to use this. And when we came to how this one, the limitations of it, it also had no limitations as per the paper source. And then there's also devlogs, which I also talked about here. Now this one was generating the 3D air from a single image using diffusion models. This one I got interest in this paper because of the 3D and how it was actually generating these 3Ds using the devlogs. And the problem was to instantly generate the detailed 3D air geometry from a single image, circumventing the need for low dimensional intermediate representation, like let us say guide strands used by previous methods that fail to reconstruct complex styles. Like for example, curly hair, that's what they use, curly hair and then afro hair, due to data scarcity. And then devlogs now in this case is going to implement an image condition diffusion transformer model employing Hawa-Grasс diffusion transformers. It models individual air strands compressed into latent codes, which the code is there, and then it predicts a high resolution, which is a 256 by 256 scalp texture map and density map. It is guided by robust Dino, of which we shall use it in. We have used it in our work, especially when it comes to our large vision model, which is the segment anything, and from the inputs and bypassing the use of 2D orientation maps. Now the problem here was the synthetic data used for training, despite its site lacks hairstyles involving braids and then accessories, ponytails and bands. Like not all the hairstyles were put, they only used a few hairstyles. And then the framework also prioritizes local hair details over perfect image alignment. And now the last paper that I'm reviewing here, the rest of the papers are all in our paper and in the videos that we recorded previously. This is the last paper that I wanted to talk about here today, which is the skin cancer segmentation and classification using vision transformer. And then this one was to develop the problem statement was to develop a rapid, accurate, and non-invasive digital system for classifying skin cancer, of which they talk of the skin cancer. They are addressing the inherent challenges of costly, time-consuming, and painful pathological analysis. And how they talk about this is that they use a two-step pipeline combining the segment anything model, which we actually use here, the SAM, that is our large vision model that we have used for high accuracy lesson segmentation which it gave the accuracy of 96.01, and with a vision transformer specifically. This vision transformer is the classifier or classification with the 96.15 accuracy. Now the model is primarily suitable for fair-skinned individuals because it is that was the limitation, because its core training data was from HAM 10,000, largely represents the white population, indicating a dataset bias, of which we are trying to fight here. And what is our problem statement? So when we come to our problem statement, we divided them into domain and then the computational problem. Now, for the domain problem is the healthcare inequality in dermatological care. When we talk of healthcare inequality here, is that in most cases, most of the systems that are out there are not applying to everyone. Okay, they are only applying. Okay, they can be used by Africans, but they don't give the right accuracy, because in most cases they mistake the black skin to be all affected area, and that gives the wrong results or misdiagnostic. And then there's bias in the global AI systems against darker tones, which I just talked about. Then there's SDG 3 and SDG 10 violations, which talk of good health for everyone and inequality solutions. And then when we come to computational problems, there's a real-time skin condition simulation on diverse tones, which is actually lacking in the real world these days, and this is what we are trying to solve here. And there's integration of diagnostic AI with 3D graphics pipeline. Okay, and when we talk of this one here, the other systems outside there which use this kind of format, but they don't put it in 3D. They just predict everything and then give you the results, and they don't give you your 3D simulations to check, to tell you the vision, where it is and how intense or how bad it is. That is what we are trying to solve here. Then there's mobile optimization for low resource settings. So our system we are developing in two phases, that is the mobile app and the web app. For the meantime, we're going to use the web app, but all we are trying to solve here is to be used in mobile applications that are as low as 2 GB RAM, 4 GB RAM. Yes, thank you. Let me get to the next. Now, what are some of our research questions? As we can see, how can AI models overcome inheritance bias? That was some of the questions that we had in our mind from the global datasets to provide accurate diagnostic for African population. And then the next question is, how can a diagnostic platform integrate precise segmentation, realistic texture synthesis, interactive visualizations of dermatological conditions while maintaining real-time rendering capabilities suitable for mobile deployment in low-resource contents? And then the next one is, how can a robust diagnostic model be developed and trained specifically for common Uganda skin conditions? How can a high-fidelity pipeline for design realistic? And so now, when we came to this, we came now to understand our objectives from the research questions. So we decided to say we are going to develop and train a robust diagnostic model for Uganda skincare conditions. And when we talk of Uganda, we talk of Africa. And Uganda will be the best because we have a variety of skin tones in Uganda, of which it will suit this system. And the next one is to develop a high fidelity skin condition simulation pipeline. Okay, and then to engineer an interactive and accessible web-based platform, as we talked about, and then to conduct a comprehensive multi-stakeholder evaluation, which we shall deal with the healthcare and the ministries involved, if necessary. And then the research contributions and outcomes. Here, so far, we have developed a skin diagnostic system based on the CLIP model that accuracy that achieves 60% accuracy and Frechet ID score of 61%. And then we train and develop a segmentation module based on the UNet architecture. We built an explainable AI module producing GrandCam heatmaps to visualize the regions influencing diagnostic decisions and providing transparency and building user trust. And then we also made a photorealistic visualization system tailored for African skin tones on a web-based prototype. It would not be a photorealistic like that, like a normal human as per now, but we made it in a way that is on the skin tones of Africans. And what is our methodology in this case? Here we are going to prompt. We made it in a way that when the user input or when an image is input, the large vision model which we have trained, here we talk of segment anything, is going to segment and visualize what the condition is. It puts out the accuracy and brings out the mask of that image. And alongside that, it also provides the ground cam module, okay, which surrounds the infected area. And this one we talked of classification. So it is also going to classify for us that this image is under this category of diseases that are being trained within the system. And then it takes the mask, and the mask is what is going to be put which the gun will pick and simulates it or puts it onto avatar, while the segmentation will just tell us that this one actually, this image belongs to this category, therefore it passes it to the user interface and is going to tell us that under this category we analyze this and this and this. And then from the segmentation or from the large vision model, which is segment anything, by the classification here we are using that is the VIT, which is the visual transformer, and then the segment anything is the large vision model. And then we go ahead. So when it does that, it's the simulated skin texture is going to be placed onto the avatar, and we shall see it from the user model, from the user interface. And yeah, this was some our data set. Talking of our data set, it's just to visualize our data set, to understand our data set. What kind of data set are we dealing with here? What as the we deal with the height, with the image size, with the image texture, which is it blurry, is it too bright, is it clear, is it too clear? Yeah, so now this is how we understand. For example, as we can see here, we understanding that we want to understand the image width versus the image height scatter plot. So we understand on this side we have the image height, and this side we have the image width, which are all above 700. And we also have the image properties correlation heat map, which tells us, we talked of the height here, the channels, the aspect ratio, the file size, and then the megapixels of that image. And the same thing here. Yeah, so now the model selection here, among the two models that we train, we chose this model. As we can see from this model here, it trained for us, but along the way it didn't give us the perfect accuracy. And we came on this one here, which encodes the image. When we input the image, it encodes that image, as I can zoom in here, and then it actually understands the patches of that image and then transform it into like 24 transformer layers, and then performs other attention, self-attention, self-attention head or understanding from the each layer that has done. And then from there it is going to extract the visual features, and it now classifies them accordingly. This is how now we have trained this. And then finally we go up to where we get the results finally in our PerformNet, the test. Here, as we can see from down here, that is now the test image that we have put, and it is telling us that is 62.00% of what has detected, and it tells us the prediction, that the prediction here is 89% confidence, and the condition it has predicted is Archie and Rosacea. That, yeah, those are medical terms. I will not get those terms well. And then when we come here, we visualize our two base models so far, the one which we understand so far. And we understand that we have the accuracy that we are with right now, 63%, and we have more accuracy to come ahead. And this is how the interface of our system looks like as per now. Might not look that big, but we shall improve it. And then we come to conclusions. When we come to conclusions, we have a lot of we have limitations. Okay, and our limitations here is that we couldn't get the right data set that only focuses on the African schemes. Instead, it is a mixed data set, and then the model would not perform because our data set also is not uh, annotated. So we are going to annotate it in the nearby future. And then there's a low model generalized ability or small dataset segmentations. And then next steps for the future, we want to focus on developing a fully annotated and curated dataset for better training on dark skin tones and also deployment of smaller, robust, resource-friendly, open field of dermatology. And alongside our acknowledgement from the source, we were clueless of what all these are or what we are dealing with here, talking of the large models, visual transformers, and that's why we acknowledge first uh, our own lecturer, that is Mr. Galwango Marvin, and then, or Dr. Galwango Marvin, sorry. And then we also talk of all technical papers. We have also cited just a few in this presentation, but in our paperwork we have cited all the platforms we have cited all of them, as we can see here, the Cargo Collab, Hugging Face, among others. Those are the ones that we have used so far, and we can see here. And thank you so much for listening. My name is Paul James, and have a blessed day.